stoichiometric condition ended up being 9.52, 0.21 O2 plus 0.79 nitrogen gives us 2 H2O plus CO2 plus 7.52 nitrogen. And we got out of this is the stoichiometric fuel-air ratio. Remember, this is fuel-air ratio, stoichiometric, is equal to 0.058. If you're wondering where did we get all that information from, the last class we just did this, right? We did this example. It says, let's say A did this, we got A, 9.52, and you've probably done a few during the homework, so you already know how to do this, and you already got the equivalence ratio of interest, or the stoichiometric fuel-air ratio. And in this case, it's 0.058. Now, we just said that phi is equal to 0.8. So that's equal to my fuel and air of my current problem divided by my fuel of my stoichiometric condition. So that's equal to F divided by 0.058, and from that I could get F is equal to 0.0464. Now, does that make sense? Yes, it has to be smaller than my stoichiometric condition because that's why we got 0.8. So this is my current fuel-air ratio. Okay, so from there, I could get how much mass of fuel that I have, how much mass of air that I have, and whatnot. So I could say M of fuel is equal to the number of kilomoles of fuel that I have multiplied by the molar mass. So that's going to equal to, I'm going to use 1 kilomole of fuel multiplied by the molar mass of fuel. The molar mass of fuel is 12 for carbon plus 4 will give me 16. So 16 kilograms over kilomoles. It's going to give me 16 kilograms of fuel that I'm going to use. Now air is going to equal to M of fuel divided by F. I already have that. That's going to equal to 16 kilograms divided by 0.0464, which will give me 344.8 kilograms of air. So if I'm trying to get my number of moles for air, Na is equal to the mass of air divided by the molar mass of air, which is going to give me 344.8 kilograms divided by 28.84 kilograms per kilomoles. That's going to equal to 11.96 kilomoles. So from that, I could write my chemical balance equation.
Bring that page down just a little bit.
Yes, yes.
Thank you.
So from there, my chemical reaction is CH4 plus my 11.96 multiplied by my 0.21 of oxygen plus 0.79 of nitrogen, and that will give me my 2H2O. We're going to have 2 hydrogen plus CO2 plus E of nitrogen, because I've got excess oxygen and nitrogen that I'm not burning, because it is lean, so there's too much air. And F let's just use F times O2. So I need to know these coefficients. So these coefficients are unknown. But if you do the balance, well, I'm putting in, for oxygen, I'm putting in 11.96 multiplied by 0.21 times 2 for oxygen is equal to how much oxygen here? So 2 plus 2 plus 2 times F. Right? So from that, F is equal to 0.51. And the same thing I could do for nitrogen. I have 11.96 multiplied by 0.79 multiplied by 2 is equal to, I only have 2E to worry about, so 2 times E. So that would give me E is equal to 9.45. Okay, so now I've got all my coefficients for my chemical balance equation. If I want my heater formation, I have to go and plug it into that equation that we wrote earlier. So I'm going to write it again here. So Q over of NA is equal to, let me just pull it off. I'm after heater formation. Or heater combustion. So what am I going to get out of this? What I'm going to get is mu over alpha. So mu over alpha is 2 H2O. Well, obviously this is in terms of number of moles. The heat formation of water plus heat formation of CO2 plus 9.45 of nitrogen, the heat formation of that, plus 0.51, bear with me here, O2, the heat formation of that, minus CH4, the heat formation of that, minus 11.96 multiplied by 0.21 for oxygen, the heat formation of that, and minus 11.96 for nitrogen. All I'm doing is just using all the heat formation enthalpies from this equation, putting it in, but now I'm using a number of moles ahead of it directly. H of nitrogen, the heat formation of that, plus 2 plus 1 plus 9.54 plus 0.51. CP of products, T minus STP, minus 1 plus 11.96 CP of reactants, T minus TST. So let's take a quick examination of that equation.
Heat of formation of water, so yes, I do have that. Heat of formation of CO2, I do have that. Heat of formation of nitrogen. So your colleague asked about this earlier, right? So what's the heat of formation of nitrogen? Zero. Yes. So this is the reason why we needed to write it in a generic form, but here, just cancel out. Oxygen. Cancel out. Oxygen here again. Nitrogen. Zero. Why are we thinking about it? There is no heat of formation. What we have to worry about is the other heat of formation. So now I could get the heat of formation of water, heat of formation of CO2, and methane. Now the question that I have is I need to find my CPs. I need to find my CPs.
On the bottom, is that supposed to be 9.45? Bottom left.
9.45. Yes. 9.45. Okay, so to get our CPs, how do we get our CPs? CP of the products is equal to the sum of all mole fractions multiplied by the individual species CP. Right? We already did this 2 lectures ago, so I need to know my mole fractions. My mole fraction of H2O is equal to 2 divided by 2 plus 1 plus 9.45 plus 0.51. And that's going to equal to 0.154. Mole fraction for CO2 just becomes algebra. That's all it is. 2 plus 1 plus 9.45 plus 0.51 is equal to 0.077. And for nitrogen, 9.45 over 2 plus 1 plus 9.45 plus 0.51, which is going to equal to 0.729. And for oxygen is equal to 0.51 divided by 2 plus 1 plus 9.45 plus 0.51, and it's going to equal to 0.039. And from that, we can stop here and